Today we're very happy to have Junho from Leuven University to tell us about log corrections to AdS4 CFT3.
Okay. Let me start by thanking Ivan for giving me this great chance to share my recent work. And I also want to apologize a bit for the lack of energy. I mean, I got a serious throat last night and I'm still relying on this spray I just got from CVS. I'll try my best, but if you have any question, please stop me anytime. So today I want to talk about log corrections in AdS4 CFT3 based on this collaboration with Nikolai, Marina, Val, and Shao. So I'm going to give you the motivation for this log problem first, and then explore these log corrections first from the gravity side, and then from the build theory side, and discuss some explicit example where I can apply the general result, and finally address some application to EFT. So let me give you the motivation first. So as we all know, one of the most important questions in our community is to figure out the path integral of string M theory beyond the two-derivative supergravity limit. This is very crucial to fully appreciate the string M theory as a quantum gravity theory, not just classical theory. AdS-CFT correspondence provide a perfect stage to explore this question. Because according to this holographic duality, the string M theory path integral of our interest around certain asymptotically Euclidean AdS solution with some internal manifold becomes identical to the dual CFT partition function. So we can use this CFT partition function to explore the string M theory path integral. And if you have certain amount of supersymmetry, you can even try to use supersymmetric localization to explicitly compute this left-hand side as CFT partition function, and then use it to explore string M theory path integral beyond the two-derivative supergravity limit. But this is very general framework, and today let me focus on specific examples of duality. AdS4 CFT correspondent arising from n stack of vector grains. In this particular case, the SCFT partition function on the left-hand side can be evaluated in the large n limit, and the leading order is well known to behave like this power law terms, and then you have logarithmic term and further corrections. And this structure has been confirmed in numerous examples by supersymmetric localization. On the other hand, on the right-hand side, you have dual M theory path integral around your supersymmetric AdS4 solution with 70 internal manifold. And you might be able to write that path integral schematically as follows, where capital X just captures all dynamical fields in your theory, very schematic expression. And then you can think about semi-classical expansion by a center point approximation, where the AdS radius is much larger than the four-dimensional Planck length. Then you have the obvious onshore action contribution, which is leading, and then loop corrections. And holographic duality tells us that these two expansions must be identical upon the holographic dictionary I presented above, relating field theory and gravity parameters. And indeed, the result from the localization has been reproduced from the gravity path integral, at least for the first three terms in many literature. The leading end to the 3F term was reproduced from the two-derivative onshore action of the effective four-dimensional supergravity theory arising from consistent truncation. And the next end to the 1F term was reproduced more recently by, again, from the classical interaction, but at the four-derivative level. And log n term was reproduced from not just classical interaction, but one-loop corrections in the gravity side. And here I want to emphasize that this log n term is really crucial to prove the quantum nature of gravitational path integral, because compared to the first two things, which is just from classical interaction calculation, this Leuven term is from one loop calculation, which is genuinely quantum calculation. This is why I want to focus on this Leuven term today. And I'm going to follow the framework of this work of Sen and collaborators about this Leuven term. But these papers, series of papers, have been focused on asymptotically flat background. So I'm going to apply similar technique to AdS4 correspondence.
Does any of these results include cases where F, the vibration, is not trivial?
So for these two, it's fine. But for this one, I'm going to comment on that issue.
Okay. But the previous check that people have done considered more general F.
Yeah, right. General vibrators.
And the Y7 in those cases, what have people considered?
So in general, when you have non-trivial fiber, usually the external manifold, you have non-vanishing gravity photon, it's fibered over your cycle, the 70 manifold. That's for all the M2 theory example I've been discussing, that's the case. I've covered in this case, but I'm going to present more general cases, but I feel like all the examples discussed in today's talk, it's like fibered in that way.
I see, but the most general kind of geometry in 11 dimension that preserve the supersymmetry one does not have to be that kind of vibration.
Yeah. The problem is, as I mentioned, I'm interested in this Leuven. But producing this Leuven correction precisely from the gravity side is quite non-trivial. To the best of my knowledge, it has been done only for two examples. First, pure Euclidean AdS4 without fibering over S7. The second example is magnetic Rydström-Nordström, Euclidean AdS4. In more general background, this one-loop calculation becomes very non-trivial because of complicated 11D background. And I'm going to explain a bit more details about this later, but the upshot is this one-loop calculation involves so-called counting zero mode of 11D kinetic operators. And this counting zero mode becomes very complicated when your 11D geometry start having like non-trivial fibering or warping, etc. So even this second example, I just put modulo subtlety there, they actually did not deal with this zero mode counting honestly. Here, there's a non-trivial fibering between external and internal manifold, and because of that, zero mode counting becomes complicated. They hide this issue and just assume that the zero mode counting can be done in the asymptotic region where the fibering goes away. So in some sense, the honest one-loop calculation we produce in Leuven is done in this single example. In other geometry, this 11D one-loop calculation becomes very non-trivial.
So this is also for doesn't involve any large k limit. No? It's like for finite k. Is it okay?
Here, I'm focusing on finite k because in the 11D background, there's a reason that this calculation is easy because in that case, non-zero mode calculation just goes away in odd dimension. But now if you start thinking about k scale like n, then the theory becomes like two-way string theory. Then you start consider non-zero mode contribution in full two-way string theory. So to avoid that, I'm going to focus on finite k.
Instead of going to the, let's say, CP3 cases.
Yeah, CP3 case in principle can be considered, but now you have to deal with infinitely many string mode. So what is our approach? I don't want to deal with 11D geometry, so I'm going to do Kaluza-Klein compactification first on the internal manifold. So instead of dealing with 11D path integral, I'm going to deal with 4-dimensional path integral on external manifold. That way, I have two immediate advantages. First, I can avoid 11D geometry, and maybe because of that, we may be able to cover more general asymptotically Euclidean AdS4 geometry. And remember that for this parallel comparison, it has been done in the 4D consistently truncated supergravity. But Leuven comparison was done in the 11D background. So if we can do this Leuven comparison in 4D using this Kaluza-Klein supergravity, now we can do this precision test all in the uniformized 4D setup. And in due process, I'm going to address some new insights on holography, non-supersymmetric molecular entropy, and constraint from EFT. But there's an immediate challenge. That is, because of this Kaluza-Klein compactification, now you have infinitely many fields from Kaluza-Klein powers. They will all contribute to this log-n term, and you cannot ignore them because this general AdS times internal manifold solution is not scale separated. So you cannot just parametrically ignore all the Kaluza-Klein powers. Their mass levels is not ignorable. So you have to deal with this issue, and I'm going to report the recent progress on this research direction. So I'm going to move on to the main part, and if you have any question, you can already ask me. Okay, so now let me move on to this log correction in 4-dimensional Kaluza-Klein supergravity. But before that, let me just quickly visualize the lack of gravitational calculation. Details are not important. Here I list the examples of 3D CFT arising from M2 grains labeled by the dual internal manifolds. Here I list the different types of 3D partition function background. Then the upshot is, once you compute the partition function on this manifold and compute the log-n correction using localization, the log coefficients seem to be pure numbers. They do not depend on any continuous parameters describing your theory or background. Quite remarkable. But as I
Sorry, what is it? Kaluza?
Yeah.
Genus. It's the
The
genus
genus,
of the
yeah. Reproducing these pure numbers from the gravity side by one-loop calculation, as I mentioned, is non-trivial. And even some check marks, there's a honest zero-mode counting issue. And the situation is the same for different types of 3D CFT, like a CFT arising from N5 grains wrapping 3D compact manifold, or theories arising from D2 grains in massive 2A theories. Seems like they all have pure number low coefficient, but reproducing that from the gravity side by one-loop calculation is quite non-trivial. And remember that these leading power law terms have some different exponents depending on the types of theories. So from now on, let me call that alpha. And now let's proceed to gravitational calculation. So the Kaluza-Klein supergravity path integral around the external manifold is expected to have the following form. And now I want to explain how to derive the C low coefficient from the gravity side. The schematic writing of the path integral would be like this, of course. Some dynamical fields X covering all fields in the spectrum. Then you set a point of approximation. In the semi-classical limit, you have onshore action here. Then for quantum fluctuation delta X, you have kinetic operator Q. Then you have this obvious one-loop determinant, which is very familiar. And of course, there will be higher loops, but today, this term is enough. But computing this one-loop determinant is already quite subtle. It has like UV cutoff issue, IR cutoff issue. And one of these issues is the existence of zero mode. That means if you have eigenfunctions with zero eigenvalues, then you get log of zero, because determinant becomes zero because of zero eigenfunctions. And it's divergent, so you need to treat this carefully. And the standard procedure by SAN is to split the contribution from non-zero mode and zero mode. Here, non-zero mode blue color terms, the prime means that zero mode are excluded. So now you can evaluate such log of determinant without any problem. Then you have to deal with this remaining zero mode path integral separately. And what Sen found is non-zero mode and zero mode contribution, both of them start contributing at logarithmic term, log n order. And for all examples I presented today, classical interaction does not contribute at log n term. So if you're interested in that C log coefficient, what you have to do is just to figure out the coefficient for this log n term from these two sources. And let me give you how the coefficients are determined for two cases. So I'm going to skip some details. But for the non-zero mode contribution, the upshot is, let's say you picked your field capital X in your spectrum. Then you know the kinetic operator Qx. Then you define this left-hand side. It's called heat kernel because this expression satisfies the conduction equation with respect to T. And then you consider small t expansion. Then you have this coefficient called Seeley-DeWitt coefficient. This is just mathematical manipulation, you can say. Then what's then found is the non-zero mode contribution has leading logarithmic term in the saddle point approximation. This coefficient is fully controlled by this fourth Seeley-DeWitt coefficient A4 and the number of zero mode of this kinetic operator Qx. This derivation takes like 7-8-ish lines. You can find it in the sense paper. I'm going to skip that. And for zero mode contribution, you can analyze in a slightly different way. But the upshot is, again, you have this logarithmic term. This time, the equation is fully controlled by the number of zero mode n. And beta is some numerical parameter you can determine by normalization. I'm going to give you some examples later. And remember that this L over square root G Newton is related to capital N by holographic dictionary. So put these two results back into the above expression and doing some massage, we arrive at this. The C log coefficient for log n term can be split into two parts. Local part, fully controlled by A4 Seeley-DeWitt coefficient, and non-local part, fully controlled by the number of zero mode of a given kinetic operator. So if you're interested in the log coefficient from the gravity side, what you have to do, you compute this local contribution A4 for given field X, non-local contribution NQ for given field X, sum them, and you sum it over the entire fields in your Kaluza-Klein spectrum according to this expression. And the Kaluza-Klein supergravity consists of fields from spin 0 to 2, possibly massive and massless. So the next task would be to determine this A4 and N for these general fields. And I'm going to start that from the local contribution first. I'm going to give you how to get A4.
Why? So is it obvious that the non-Kaluza-Klein states can be just ignored?
Good question. And 11 the case, that is true because this so in this expression, like for example, if you start consider M theory, you might have 11 supergravity fields, but that could be like the spectrum we don't know well. Like for example, even for string theory, we don't know the first spectrum. But this expression, when you derive this, you can show that this term, A4 term, just goes away in odd dimension, like 11-dimensional background or something like that, 4-dimensional background. In 4-dimensional background, it does not go away, but 11-dimensional background, it goes away. So the approach is you start from full M theory on 11D background, but you know that you can ignore non-zero mode, full non-zero mode contribution for 11D fields with massive fields. So you can start from 11D supergravity. So you completely ignore non-zero mode in 11D. So focus on massless fields in 11D and then do Kaluza-Klein compactification. That's the logic. I just skipped that. So I want to compute A4 for fields from spin 0 to 2. For that calculation, I'm going to assume two things for simplicity. First, I'm going to assume that the kinetic operator for your field x takes the Laplace form. Like the second derivative is fully Lorentz contracted with some possibly non-vanishing field strength omega. And then I'm going to assume that the background of our interest is Einstein. Like you don't have non-vanishing background for a photon, but it can be turned on later. For now, let me focus on this special case. Then, thanks to the first assumption, you can refer to this Hit-Corner manual paper. Then that Hit-Corner manual paper tells us that this A4 coefficient of our interest can be written in terms of this trace expression, where all the expression can be read off from the given data, like E is from this kinetic operator, R is the Ricci scalar of the background, E4 is the Gauss-Bonnet density of the background, W is the Weyl tensor. Then, thanks to the second assumption, you can explicitly evaluate this trace over field space. Here, field space means like if you have Dirac spinor, you have to integrate over spinor indices. Then you arrive at the following Hit-Corner formula, where pink-colored coefficients are dependent on the field content because it's a function of kinetic operator. But the cyan-colored terms are full derivative terms on the background, so it depends on the given geometry. Here I ignore the boundary terms, but in our paper, we investigate the boundary terms carefully and check that they do vanish for all types of geometries we consider upon holographic renormalization. But today, let's delete us and proceed with this formula. So it seems like the next task is to determine this coefficient for fields from spin 0 to 2. Then it seems like we are done. But of course, we have to check if these assumptions are satisfied to rely on this formula.
The E terms and omega terms just goes away when you do the trace.
E terms.
E square and omega square term.
Oh, E and omega are in this kinetic operator.
Or they're related in terms of the curvature.
Yeah.
Okay.
And yeah.
Correct. So they contribute to the E4 and W square and R square terms.
So they can be written in terms of linear combinations of these four.
But that's presumably because you're looking at supersymmetric background.
Oh no, I mean this expression does not require supersymmetry.
I was just asking so the terms like E square, when you do the sum, somehow it's related to a combination of E4 and W square and R square.
Yeah. So this expression,
but E could come from the like the curvature of the background gauge fields, for example.
Oh, here, yeah. Here, that's why we focus on this Einstein. So for Einstein case, these three are the only options, and that's enough for linear combination. For non-vanishing background, like for
example, the twisted, yes.
Yeah, like RF square.
Okay, good.
Now, let's see if these assumptions satisfy. Consider massless spin 1, our friend Maxwell. So Maxwell field here, and we are doing path integral, so we have the gauge fix. You can read off the kinetic operator for quantum fluctuation. It's given like this, and it's satisfying the Laplace type assumption. So we can use that Hit-Corner formula. But once your field, spin 1 field has mass, then you have Croca action, and you cannot gauge fix, it's not gauge symmetry. And the kinetic operator is now not Laplace type. You have this non-contracted second derivative. So we cannot directly apply the Hit-Corner formula here. And same thing happens for spin 3 half, spin 2 massive field. So we need some way to circumvent this issue. And what we found is the answer is in like 100 years old subject, so-called Stueckelberg formalism. when you have massive spin 1, the proper prescription is you include scalar Stueckelberg field capital B here. Then these two terms now have new gauge symmetry, and you can add this gauge fixing term. And the kinetic operator for spin 1 fluctuation and Stueckelberg field becomes like this.
So it's mu plus m d mu b, right? It's the gauge fixing.
Gauge fixing term, oh wait, it's all.
Or is d mu plus m b?
Yeah, I think there is an obvious typo somewhere. Yeah, indeed. I need to check, but probably yes, d mu is necessary. Anyway, I should fix it. Of course, it's not correct. But once it is fixed, then you can read off the kinetic operator, and it satisfies the Laplace type condition. And you can do the same Stueckelberg formalism for massive spin 3 HEP and spin 2 field, and use the Hickman formula. And then we completed the calculation for all fields from spin 0 to 2, both massless and massive. And this red colored massive spin 1 through HEP 2 are new results in our paper. Haven't been done yet. Haven't been done in the previous work. And I emphasize that the contribution from Stueckelberg fields are non-trivial. You see, I split the contributions, and they are not smooth. Taking m to 0 does not smoothly connect to the massless case. So you might be worried about if this prescription is the correct way to compute the Hickman coefficient. I'm going to give you a very non-trivial evidence that this is the proper way to compute the Hickman coefficient later. But for now, if you believe me, then we are done with the local contribution. Whatever the Kaluza-Klein supergravity is given, you know once the spectrum is given, you just use this table to compute the Hickman coefficient for each field and add all of that. Then you get the full A4 coefficient.
Of course, ideally, you would like to change the gauge fixing, say, take psi gauge and then check the results on the dependent psi.
So the issue here, what you need to understand is, of course, if you change gauge fixing c over 2, then this structure is broken. Then the point is you cannot use this formula. But of course, if you just do one-loop calculation by properly counting eigenvalues and degeneracy and do proper regularization, you should be able to do this calculation. Here, this specific choice of gauge fixing, that one and this one, is just designed to use this Hickman formula.
Yeah, to remove the mixing between the scalar and the vector.
Okay, and let me briefly comment on the non-local contribution.
So for the scalar, I mean, where is the information of the boundary condition in this calculation?
Oh, here, I did not provide anything about boundary contribution, but
For the boundary condition, like in AdS4, there are standard, there are alternative boundary conditions for
Yeah.
field.
yeah, for this,
Is that going to change the zero mode contribution?
oh yeah, it's for that to ignore the boundary contribution, it has, for example, for scalar, both Dirichlet or Newman or mixed boundary condition are all fine. I mean, for all cases, you can just show that upon the holographic normalization, it just goes away. And for other fields, you can also analyze what kind of boundary conditions are fine. The only remaining solvable issue is spin 2. For spin 2 case, the boundary conditions is very well known to be complicated, and we cannot honestly prove from the scratch that for a reasonable boundary condition for spin 2 fields, the boundary condition goes away. We couldn't prove that, so we left it for future technical work. But at somehow, under that assumption, we got this table. So in some sense, this is assuming that the reasonable boundary contribution for spin 2 fields do not change this result. we just assume that. But at the end of the day, I'm going to give you that these data is correct by a very non-trivial consistency check. So I think at the end of the day, it should be fine. But
yeah, I see. But just to be sure, so you're saying that, for example, for scalar, when you are in the mass range, you can pick, but you can take both alternative and standard quantization.
Yeah.
It will not affect the answer for this zero.
Yeah. Okay, for non-local contribution, let me be quick. So this beta numerical parameter, as I mentioned, is just determined by path integral normalization. I'm going to skip the derivation. You can refer to that paper. It's just numbers for spin 1 through half 2. The real deal is the zero mode. It has to be analyzed for a given background case by case. In our paper, we consider pure Euclidean AdS4 and AdS2 times Riemann surface. For now, let me just briefly talk about pure Euclidean AdS4. Already 30 years ago, Camporetti and Higuchi found that number of zero modes per spin 0, 1f, 1, 2 are 0. Only two form has zero mode. And we found actually there's a spin 3 half zero mode. Like if you start from eigenfunctions for spin 1 half field, like this, you add the supercovariant derivative here, you construct some spin 3 half field, psi star, and you can prove that this psi star is zero mode like that. The problem is, any psi star constructed in such way has vanishing norm or not square integral. So again, the spin 3 half zero mode turns out to be 0 again. So pure Euclidean AdS4, there is no zero mode for Kaluza-Klein supergravity because two form is not in the spectrum. Of course, you have to do this for different types of geometry, but once that fact of life is accepted, now we are done. To get the low coefficient for 40 Kaluza-Klein supergravity path integral, you first compute the local contribution by evaluating this A4 coefficient based on the heat kernel formula using the table I provided, and then compute the non-local contribution by investigating zero mode, add these two, and sum it over the full spectrum. But as I mentioned, this sum over Kaluza-Klein tower is always infinite sum, so it's quite complicated. So before doing this direct calculation, I want to show you the implications of the localization result based on holography. It turns out that we can do a very strong bootstrap. Remember that the coefficient C from the holography side, the CFT side, was always a pure number. Like I consider three different types of partition function: squashed sphere partition function, topologically twisted index, superconformal index, with dual four-dimensional background listed here. But 3D partition function always have pure number coefficient here. So they did not depend on any continuous parameter describing this geometry, like squashing parameter, magnetic charge, or electric charge, or rotation. They do not show up in this low coefficient. So what does it mean? So the C low is independent of continuous parameter. The non-local contribution also does not depend on any continuous parameter because it's from counting zero mode. You cannot get any number depending on continuous parameter by counting something. So the total local contribution, that blue one, should also be pure number. It should not depend on any continuous parameter describing these geometries. And that will give us the following constraint.
Is there a simple formula? So go back to the previous table. Is there a simple formula in terms of C log, just in terms of the module invariance of the three-dimensional boundary manifold?
Oh yeah, so this, I'm gonna tell you that later. This is actually precisely minus chi over 4.
Exactly.
Yeah, chi is still
Okay.
not.
So it's just given by the bulk order number.
Yeah.
The bulk left field thing.
You mean the Euler characteristic?
Yeah. So,
So you're assuming that sigma is oriental or something. C, I mean, sigma is, I mean, you cannot have cross cap or something.
So here I did not assume anything because I mean I just considered 3 examples and computed the log equation for that case. Then it is given like that, and it turns out to be like minus chi over 4 always. But
Sigma sub g can be non-orientable plus.
Sigma of g.
Here it has to be supersymmetric.
Has to be oriented.
Yeah, here, yeah, these are all supersymmetric and very well-known structure. Otherwise, we cannot use localization. Now consider this total local contribution from the gravity side. And now the backgrounds have non-vanishing gravity photons, so 3 terms are not enough. And you need to add this RF square term there. And of course, there would be more full derivative terms, but using equations of motion, of background, and field derivative definitions, you can rewrite them into these 4 combinations. Then the squashed Euclidean AdS4 case, the total local contribution written like this, it has to be independent of squashing parameter for the reason I explained. And you can do the same logic for supersymmetric Reisner-Ostrom, supersymmetric Kerr-Newman case. Then the final result should be independent of continuous parameter. And we solved this constraint and found that CB1, B2, when it's summed over all fields in the spectrum, it must be 0. Otherwise, these conditions cannot be satisfied.
Sorry, I missed. Do you have an argument for these bootstrap conditions in the first place, or are you just working assumption?
Well, this is the conclusion from holography. So in the CFT side, C is independent of continuous parameter, and non-local contribution that
You're using supersymmetry.
Yeah.
You're using supersymmetry.
Yeah, I'm using supersymmetry. But what is the interesting thing is here, indeed, I'm using 3 supersymmetric background to derive this constraint. But once you get this constraint is not about geometry, it's just about field content. So this constraint should be satisfied for any 4-dimensional Kaluza-Klein supergravity supposed to be dual to n equal to s CFT. This is our bootstrap conclusion. And you might ask about, what about this AE coefficient? This AE coefficient is not necessarily 0, because when you integrate this E4 Gauss-Bonnet density over the background, it gives you Euler number. And that's number. That does not depend on continuous parameter. So the contribution from non-zero AE coefficient is given like this, and it does not break the conclusion from holography, so it can survive. But already this constraint seems quite strong. And remember that I presented how to compute such heat kernel coefficient from the gravity side by heat kernel formula. And we need to check that, if this is truly the case. In our paper, we consider many examples, but today let me just provide 1 example to check this. N equal 8 Kaluza-Klein supergravity from compactifying 11D supergravity on S7. What is the spectrum? For this supergravity case, spectrum is N equal 8 supermultiplet, labeled by Kaluza-Klein level N. Massless or massive, but countably infinite. Then this ACB1 coefficient receives contribution from all this spectrum. B2 I cannot compute because for the gravitational calculation I assume the Einstein-Maxwell. So let's focus on Einstein case. Then by tedious calculation, we found that heat kernel coefficient C and B1 vanish level by level for all integer n. So at the end of the day, the sum of C, B1 over entire tower, of course, they have to be 0, and it's consistent with the bootstrap. And you might think, well, isn't this calculation quite trivial? It looks just 0. And I want to say it is not. To show that, I prepared this slide. So the Cn means the contribution from nth level multiplet to C coefficient. First line is from contributions from scalar, spin 1/2, spin 1, spin 3/2, spin 2. Here, dimension means the Weyl dimension formula for various representation in the multiplet. And see these red color terms. They are not zero only when small n is greater than or equal to 1. In other words, when the fields are massive. They are contributions from Stueckelberg field. If you do not include these 3, you don't get 0. Only when you get at these 3 terms from Stueckelberg field, you got perfect 0. So I think, no, not I think, it's true. This is the very non-trivial evidence that the calculation based on Stueckelberg formalism gives the correct answer. So since so far so good, the expectation from field theory side is consistent with gravitational calculation, but there's a remaining piece. You might remember we have non-vanishing contribution from AE. So to analyze that, consider the path integral over pure Euclidean AdS4. Then we know, I mentioned that there are no zero mode, so we can ignore the non-local contribution. And C and D1 vanish, I mentioned. So the only source of low coefficient is AE coefficient. And this also gets contribution from all multiplets. So in general written in terms of this infinite sum. Obviously diverging, but the problem is from the localization side, in the dual side, we know that the answer has to be -1/4. And it's obviously different. So at this point, I want to introduce 2 options. First, do the regularization by following the well-known method. Like this combination, I don't know exactly why, but this infinite sum expression turns out to be exactly the degeneracy of Laplacian on S7. So you can use the spectral zeta function regularization to regularize that, then you get 0. If you follow other 2 methods, like in this literature, we also got 0. And 0 is well known to be not the same as -1/4, so something's going on. Holography is not working. But if that's the case, the answer might not be that surprising. Like here, I'm assuming that I started from Kaluza-Klein compactification of classical theory, and just implicitly assuming that it's valid even at 1-loop level. But maybe that's not the case in the first place. Like, for example, I completely ignore the 11D ghosts. I just consider 40 ghosts. So if you consider Kaluza-Klein tower of 11D ghosts and consider their contribution to loop level, they might be responsible for this missing -1/4. That could be the case, but what I want to emphasize today is more brave option 2. Just motivated by holography to make this match work, let's assume that this infinite sum is somehow regularized to yield A = 1/6. It's designed to make -1/4. Of course, by itself, it does not tell us anything because it's just choosing the regularization scheme by hand. Then we have some interesting consequences. That is the following. Now, using this regularization scheme, we can try to compute the low coefficient for generic background, not pure Euclidean AdS4, for general asymptotically Euclidean AdS background. Then the result is -chi/4, because as I mentioned, AE is the only source. C and D1 just go away. Here, the hidden assumption is that there is no zero mode, even for general asymptotically Euclidean AdS4 geometry, not just pure Euclidean AdS4. It's a very strong assumption, and we don't know how to prove that yet. But let's accept it for a while. Then, if you consider supersymmetric backgrounds with non-low coefficient from the holography side, field theory side by localization, the result perfectly match. Because the field theory side result, as already pointed out, it's always given by minus chi over 4 for squished sphere partition function, twisted index, and superconformal index. So the gravity and field theory side look consistent. And if you consider non-supersymmetric background, in that case, we don't know the law equation from the field theory side. So now we can make a prediction. Like if you consider AdS charge black hole entropy, from this minus chi over 4 from the gravity side, we know that the Leuven coefficient should be minus chi over 4. Chi is 2, so it has to be minus 1 over 2. And by translating this n to the gravitational parameter, you get the log of area contribution to the black hole entropy.
But isn't this a bit dangerous? I mean, there is one regularization scheme that tells you that this coefficient is 0. You could try to say that there's a supersymmetric scheme that tells you it's going to be 1/6. That's going to be matched with the supersymmetric case. But then there's no a priori reason for a non-supersymmetric case that would be the useful principle that would take the scheme.
Yeah, so
you have to argue somehow the scheme dependence does not affect the log n coefficient.
Scheme dependence.
Yeah, here it's clear because you have supersymmetry, and then supersymmetry takes which is just scheme.
Yeah, supersymmetry.
But you can test what happens when it's not supersymmetry.
Yeah, if the scheme depends on the fact that your background is supersymmetry, then of course you cannot justify this.
Yes.
Here, what I'm saying is, if just believe that A is 1/6 regardless of the supersymmetry, then you get this.
But why would you do that?
Oh.
So is there any cross-check for this non-supersymmetry?
Yeah, so this is just prediction based on the scheme choice. I mean, it cannot go
There's
beyond
nothing to
that.
be compared.
Yeah. Okay, so far I just delivered a message from the top-down holography side, but in the last slide, let me change the gear and see what this bootstrap means in the context of bottom-up approach. Just in one slide. It could be a bit heavy, but let me try my best. Consider a four-dimensional theory consisting of general relativity coupled to finitely many fields. And then assume that it has at least one AdS vacuum, and it also has UV completion beyond certain energy cutoffs. That is basically assuming that your theory is standard EFT in AdS4 for a certain quantum gravity theory below the cutoff. Then, through the putative quantum gravity theory, you can imagine dual 3D as CFT, and now you assume the critical statement. Let's assume the partition functions of this 3D CFT have pure number logarithmic coefficient. Then, and this statement was, as I mentioned, confirmed in numerous examples for n equal to supersymmetric cases. But supersymmetry itself is not the key. Let's assume that the logarithmic contribution has pure number coefficient. Then we can do the bootstrap argument and derive the same constraint. C(b1, b2) hit kernel coefficient for our standard EFTT has to be 0. Otherwise, okay, I can explain what happens otherwise here. The conclusion is that these three hit kernel coefficients vanish for generic Einstein-Maxwell background. So what does it mean? If your putative standard EFT has non-zero element out of these three, then there are only two options. It cannot be a valid EFT, or its dual CFT introduced in this step 2 must have some coefficient for logarithmic term that depends on continuous parameters.
Are you saying again why that's exotic?
So, to the best of my knowledge, in 3D CFT, we have never seen a partition function whose logarithmic term has coefficient which is not a pure number.
But that's because you can only compute it in the supersymmetric case, right?
I mean, just for example, even without supersymmetry, like CT coefficient, CT or something like that. Not actually here. I just focus.
But if you're talking about coefficient of log L, CT does not appear there.
What I mean is CT can be obtained from the second derivative of the partition function with this quotient parameter.
Yes.
And it turns out to be CT does not have this type of low coefficient as far as I know.
That's right, but CT you can only compute for supersymmetric case or free theories.
Oh, the second derivative relation does not depend on supersymmetry, right?
Sure.
Yeah. So my point is CT in CFT, even without supersymmetry,
With holography dual.
Yeah, here, yeah, of course, holography has to be assumed here.
Yes.
But CT, it does not seem to have that logarithmic term. That means it's if you go back 2 steps above, like the starting squash sphere partition function,
Yes.
it has to be its coefficient should be like at most linear in squashing parameter. Otherwise, when you get second derivative, you get something non-zero. So when you don't have supersymmetry, you can use that argument to arrive at the same conclusion. Like in that case, you don't get this strong constraint, but like certain constraint on this heat kernel coefficient, and you can. That's one argument for case without supersymmetry, and you can use another argument I can comment on later.
But you're talking about specific continuous parameter dependence that come from squashing, right?
Yeah.
Because there could be other continuous parameter in your theory.
Yeah.
It could be a couple of manifold, for example. But that doesn't matter for this argument.
Yeah. Exactly. And then, for example, for the n equal 2 4 gauge supergravity, it has non-biasing C coefficient, so you cannot avoid these two classifications. That's one of the core messages I wanted to deliver in this slide. And let me now briefly summarize and provide some future directions. So I consider low corrections to Euclidean path integral of 4-dimensional Kaluza-Klein supergravity. We mainly focus on local contribution, governed by A4 coefficient. I explain this A4 coefficient is controlled by 4 heat kernel coefficient, and they could be studied by introducing Stueckelberg fields when your fields are nested. And now, from the field theory side, I bootstrap 3 out of 4 coefficient and confirm this in specific example by gravitational calculation, and also discuss some constraint on EFT based on the same bootstrap argument. And I briefly comment on non-local contribution, emphasize that the zero mode has to be analyzed case by case, and present just one example today. For future directions, so about local contribution, you remember that the gravitational calculation side, I did not provide B2. The reason is we couldn't compute the B2 coefficient for spin greater than or equal to 1 on generic Einstein-Maxwell backgrounds. It's quite complicated, so that's one technical feature question. And then confirming this bootstrap constraint from field theory side for generic n equal to supergravity theory by honest gravitational calculation is also a remaining task. And more interestingly, what is the proper regularization for this thing? I mean, I did not provide any physics-wise or mathematical-wise, honest argument. I just provide 2 options because as far as I know, there's no perfect answer from the scratch. So this is obviously interesting question. And for non-local contribution, I think the first and foremost question is how to do this zero mode analysis in more general asymptotically Euclidean AdS4 geometry. Like for pure case, we could do that, but what if it's not pure Euclidean AdS4? It's quite difficult. So this is the remaining question. And finally, about the EFT, remember that the key statement is somehow we need to argue that the logarithmic contribution to the partition function should be pure number. When you have supersymmetry greater than or equal to n equal 2, you could do the by localization. But what if we don't have supersymmetry? So there's no proof for that, but there are some possible directions. One is what I just mentioned to be found. The other one is the 3D thermal effective action due to AdS curve geometry. So the 3D geometry S1 times S2 with thermal cycle dual to AdS curve is not supersymmetry, so you cannot compute partition function on that geometry by localization. So in principle, you cannot argue that logarithmic coefficient is pure number. It's very difficult. But recently, these great people suggest the approach to compute such partition function using thermal effective action. And if you can investigate this thermal effective action more carefully, and if you can argue that this low coefficient is truly pure number for this geometry too, then you can use that result for this EFT argument about bootstrap. But this is, of course, an open question, and it would be very interesting if we can make this argument more solid based on this approach. And that's all I prepared today. Thanks for listening.
In a non-supersymmetric case, how do you argue this coefficient of log is not contaminated by something else? For example, something from log squared. Well, so you have the log squared, and this coefficient is contaminated by how you define UV cutoff.
Log squared, I didn't.
For supersymmetric case, you know those terms do not exist. But for the non-supersymmetric EFT, I mean, there are infinite non-BPS terms you can write in your effective Lagrange effective action for the supergravity. For supersymmetric case, they do not contribute, so you have very clean power law corrections. But for the non-supersymmetric case, there are infinite number of terms already from the on-shell action that could contribute. And you can imagine it could give some term like log L squared.
Yeah, so I think what is actually essential to go with this argument is in the CFT side, like you can imagine like log square or whatever very complicated terms. But I think the upshot is, at the end of the day, what you want to bootstrap is the heat kernel coefficient in the gravity side, right? So you don't need to understand the coefficient of many other terms like log square, like log to the 3, or even more complicated terms. I may not be interested in all of that, but some of that, if it's related to the...
I was just asking about phrasing this question. So if the coefficient itself is ambiguous, then it doesn't make sense to ask the coefficient to be a pure number.
In what sense it could be...
If it's contaminated by something else, that depends on the scheme choice. If there's log L squared term, for example,
yeah, log L squared,
then the coefficient of this will be contaminated by how you choose your UV cutoff.
So log L squared, you mean L square log L?
Log L, whole thing squared.
Yeah, but then it's 2
yeah,
L.
it's log L squared.
Log L, everything squared.
Mm-hmm.
But what I mean is that's another term in the expansion, right? I mean,
but for supersymmetric case, you don't have that term. Right? You just have power law, they have log.
Yeah, supersymmetric case, we don't even have that. In
That's
general,
right.
we might have that,
Yes.
like log L entire square.
Yes.
But my point is, now you want to compare this expansion
Yes.
possibly with real terms
Yes.
in the gravity side.
Yes.
And in the gravity side, what I want to bootstrap is the heat kernel coefficient controlling log L and log L term.
No, but if you have log L squared term, it's log L over epsilon. So depending on your choice of epsilon, the term will shift. The linear log term will shift.
But that, like for example, epsilon, if it changes, it of course it affects the order 1 term, but the coefficient of log L term, it's independent of shifting this UV cutoff, right?
But if you have log
You
L,
have log L
to the
squared term
square
will shift.
and you shift epsilon, you affect the terms 1 order below and so on.
Ah, I see. Yes,
I think you're assuming a particular expansion of the EFT dependent function for the holographic theory in this in a large L expansion.
Yeah, I see. So you're saying if you have log L over epsilon entire square
Yes.
term, then the UV cutoff sensitivity
Yes.
could be an issue.
Yes.
I didn't think
I
about
think
it.
then this question becomes ill-defined.
Yeah, I see. That's a very good question.
which is related to the other way of rephrasing it is how the 1/6 depends on the scheme.
Exactly. Yes. For the supersymmetric case, that term is not there, so you're okay.
The two things are related.
Yes.
Yeah, I did not have an answer for that. It's a very good question because thanks. Yeah, we can also discuss about it now.
Do you know if one wanted to study 4D backgrounds with some singularities like spindles, maybe the spindles that in 10 dimensions become regular, right? How would you do you have a method, the idea of what to do?
If the spindle in 4D, of course, not in 10D, is now not regular. So if someone is against considering a path integral around such solution, then we cannot apply this. But if we accept path integral around such 4D background with some, I think it's not that bad. That regularity issue is not that bad. Like it's like orbit for right? So if someone accepts the path integral around such classical solution and accept the set point approximation around the solution, I think the logic can proceed in the same way.
I'm curious about these cancellations in less supersymmetric cases. You had shown that n equals 8, that the cancellation happened like level by level.
Yeah.
Is that true for other cases with less supersymmetry? Can one make an EFT argument about how these cancellations must happen?
Yeah, I do not have EFT argument for that, but for n equals 6, we also confirmed but once your supersymmetry is less than like n equal 2 and 3, this confirmation becomes very complicated because now your spectrum not just have this Kaluza-Klein label, but there are a bunch of flavor symmetries, and you have quantum numbers for these flavor symmetries. So you have to sum it over that too. So the infinite sum is now not just sum over one integer, but like 2, 3, 4 integers. And as far as I know, there are not the regularization for such multiple infinite sum is not well established. So we couldn't check the zero appropriately. So that's why we left this question 2 as a future direction. It's quite non-trivial.
And in some of these other cases, it already requires summing over the whole tower.
Yeah.
When you can't do this.
Exactly. Level by level vanishing is not happening anymore. So
Any more questions for Junho? Let's thank Junho again. You're familiar with the spindles?
Yeah. When I was in